Hello, everybody. I'm Pascal Elahi from the Pawsey Supercomputing Center, and I will be talking to you about the migration module number 4, installing and maintaining your software for our new supercomputer, Setonix. So the focus of this training is to discuss the considerations and best practices of installing and managing your own software stack on Setonix, and identifying the impacts and considerations for your current software stack when migrating to Setonix, what you have to do to migrate that software. We'll also discuss the software stack development tools, profilers, and debuggers in this particular module. So when and how to install software. So the software stack on Setonix provided by the hardware vendor Cray, as well as the Pawsey staff, is meant to be extensive, but it's not fully inclusive. So obviously we will not have every bit of software that you may want. And it's organized in sort of 3 levels. So there is the system-wide software located in /software/Setonix. This is accessible by all users. It's just accessed through the module system, and it's maintained by the Pawsey staff. This is where the software, if possible, is optimized for Setonix hardware. This software typically includes, definitely includes compilers, high-performance libraries, and some set of research domain-specific software packages, some debuggers, and profilers. Users are part of projects, and projects can have also their own project-wide software installations in /software/projects/project ID. Of course, project ID here would be the particular project that you belong to, such as Pawsey 1, Pawsey 2, etc. There's also user-maintained software. We suggest that if you're doing any specific stuff for yourself, to have that in /software/projects/project ID/username. This is obviously where you should maybe keep downloaded containers that you're going to run, and any slightly smaller projects that are not necessarily like smaller software that's not meant to be project-wide for your group. The details of the software stack and software stack policies are available on documentation. We are going to now be focusing specifically on how you build your own software. So the best practices for building your own software is to, one, located in the software file system. This was previously group, was used for this purpose. Occasionally, some people used Home, but Home has got a very small quota, and so should not be used to store software. For software we do not provide, the recommendations are to try to use the Spack package manager. So Pawsey has deployed our software using Spack, a package manager, to build software and produce module files. So we recommend using people to use that for software that we not provide. For software that has a complex build process that has very specific versions of libraries to use, you can try to use containers. Containers can be a good way of, they might be ones that exist, but could also be generated. For Python and R software, we recommend using pip, Conda, and R package managers, so not Spack. Otherwise, you'd have to manually build software using tools such as GNU Make and CMake to build from source. The information on Spack, containers, and package managers are found in this module. So the first step is to, one, review the Setonix modules to see if that software is present. Currently available modules can be searched by module avail or module spider. You can see more details in the previous migration module number 3, using modules and containers, as well as our documentation on modules. So module avail might say, well, I want to use HTF5. This happens to be an IO library. Instead of building your own, you could see if the version you want is available on Setonix. So an example is shown here. You can see module avail. It will point to some Cray provided modules, so Cray HTF5, Cray HTF5 parallel, but also a large number of HTF5 interfaces provided by Pawsey that support different APIs and different parallelisms, or should say, at least in HTF5 case, parallel and non-parallel, along with some containers that might contain some HTF5, right? If the module doesn't exist, an example would be Vim, doesn't happen to be in a module. You could then try using module spider to find if it's anywhere in the set of hierarchies, anywhere in the modules. And if it's not there, then that's when you'd go, okay, I really do need to build this software because I need it and it's not provided by the modules. So we recommend using package managers to install unavailable software. So Spack, this package manager, has an extensive list of recipes for over 5,000 packages. You can check recipes if a recipe exists, and then check its information and see if a fit for purpose version is available. It's possible that the particular version of the software is there, but perhaps the particular build you're looking for is not available. But if it is, then you can build the package and generate a module as well with Spack. Containers was over SHPC provides over 300 containers designed for deployment on HPC systems. Containers for HPC, what this does is essentially provide a module that provides easy access to the software that resides in the container. So you could check to see if that container is available, looking on the particular site. And if it's fit for purpose, then you can grab this container and then deploy it on the project or user part of the software tree and run there. Pip and Conda obviously have a very extensive list of Python packages, which is enormous. To see that a package is available, you'd have to go to pip.org, and if it is available, install it with pip. Conda also has a large number of packages which you can search for. So the Conda package manager is a bit more complex. It does more than just Python. Pip is kind of focused on Python. So R, which is another interpretive language, you can check to see if a package is available on the R CRAN site. You can search for it by name, or you could try to use Conda to install it. So building with package managers. So Spack, I've mentioned it before, but what is it? So it is a package manager designed to deploy software on HPC systems. It's really the aim to do this type of deployment. It replaces Mali, our previous package manager, which was in-house. But Spack is used by a wide variety of computing centers and is undergoing heavy deployment. It provides, I can't remember the number of packages now, but I mean, it's well over 5,000. And it has a very user-friendly CLI, command line interface. And probably most useful for most people is it automatically determines the dependencies of a software and then will build them. So an example of if you ask Spack, I want to build Gromax, happens to be a particular bit of software that we do provide, but if you ask Spack, how do I build Gromax, it would tell you, well, Gromax actually depends on these packages that depend maybe on other packages. And then it will then start building from the bottom up every single package that it needs. You'll notice one example here of Cray MPitch. I will mention it again a couple of times, but because MPI, this distributed memory, is quite specific to the hardware, we highly recommend that everybody uses Cray MPI to provide this interface for distributed packages that use distributed memory and multiple nodes. There's way more information on Spack at their website, so please feel free to browse that. It's very well documented. So building software with Spack, so we have a module that provides Spack, so you do module load Spack. You would have to provide the version. The version happens to be 17. And then with that, you can then write commands such as Spack info, a package name, Spack spec. Spack spec essentially tells you what it thinks it needs to build that package. So an example here is Nano, which is a little editor. So if you ask Spack info, it tells you the description is a tiny little text editor. It tells you the versions that might be there. And then you could ask Spack to figure out how it would build it. And here's an example of the build. And then you can install in this appropriate directory. So we've set up the Spack module and some configurations to install software in the appropriate location. So to install software with Spack to your user space in the project directory, so SAS/software/projects project ID/username, you would just run the command Spack install the package name and the variants. To install software to the project space, it actually requires using a wrapper script that we provide, which is Spack_project.sh, and then install package name variants. And then it will install that bit of software in that the project space where everybody has access to it in your group and in your project. So Spack can also generate modules, which is quite useful, right? So you can install software and then ask Spack to produce a module so that later on you can just do module load, as opposed to having to look at that directory and then figure out what you need in that directory. And the reason this is very useful is that Spack tries to make sure that it constructs a unique name for every install, which is dependent on all the dependencies that the package has and all the compilers it uses. These directories can be quite long. You can see it's if I do Spack install GSL, the directory that it constructs is GSL, the version, and then a quite complex hash, unique hash, as unique as it can be, and then it'll install everything there. So instead of trying to look at this and then explicitly adding this path and any internal directories such as include and lib and binary to the paths you need for your subsequent builds, you can have or subsequent use, you can have Spack generate a module that will then provide easy access to all of this. And the idea would be to then Spack module lmod refresh. You don't have to have the -y, but the idea is this says, yes, please rebuild GSL, and it will then construct a library in the appropriate space for you to do then. If you then use that path, you could then module load a particular that particular module. It's always got an extra little hash to it. So GSL 2.7 and a hash, and you would see that this is slightly different from the modules that we provide, where if we do provide GSL, usually it would just be GSL and the version and not a build hash. Again, more details of how Spack does the module construction and some configuration options are available on our documentation and also on the Spack website. So how to pull and use containers the traditional way. So pre-Setonix, we provided the Singularity module, right? And that Singularity module provided Singularity, which would then be able to run containers. You could pull containers from a particular place and then run it with explicit commands, right? That's still available on Setonix. So you would module load the Singularity, you'd load the Singularity module. You could then load a specific or download a specific container, such as Singularity pull. And this happens to be loading Blast or downloading Blast to the local directory. And then you could then run this container and the commands that exist in this container by Singularity exec blast help in the package name. So that's still perfectly valid. It works just fine. You can also use SHPC. So what is HPC in container modules? Well, a container module allows a containerized application to be run with the same commands as if it's not containerized, as if you had it just installed in your normal paths. Right? It uses command wrappers and shell functions or scripts to do this. Singularity registry has a much smaller selection of containers than all containers that exist, but it's provides a very, very nice user interface. Right? The subsequent thing is that you just module load something and run a command. So the set of recipes is growing. There's currently about 300 plus. It supports Singularity, Docker, and Podman. We are currently just focusing on Singularity on Setonix, and it supports the production of lmod and environment modules. And recipe writing is easy. There's some information on how to write recipes. The list can be found here at the Singularity Hub, Singularity SHPC, or sorry, HPC. And here the idea would be to install something. So you'd module load SHPC. So it would provide you that package manager. And then you would tell SHPC install the container and the version. So container name and version. And it would then install it in your user path. And then if you make sure you have that, I mean, by default, it'll always search for modules in a particular place. You could then module load that container with the version and then suddenly do the package command as if you had it just a normal module. So the example would be that we had above was Blast, right? We had to Singularity Blast, we had to do Singularity exec, the particular container, which happened to be quite a long name, .sif, and then Blast P and some commands. In this case, you would just run the module load container name, so Blast P, the particular version, and then just write Blast P as the command name. So it simplifies the use as well. So how to install Python packages in pip? Python packages, we would use pip and Conda. This is a recommendation. We do not recommend using Spack for Python or R or possibly some other interpreted languages as well. So for using checking to see if packages are available, you have to, for Python, there's the sites that you can check. So the Anaconda and pip sites. To install software for pip, it would be pip install. You put in -- user, so it install in your software project's user space name, and then the package name. And then Conda would be something similar. Again, just to reiterate, do not use Spack to install Python packages or interpreted language packages. Pip and Conda are better suited to this purpose. So an example would be you'd load the pip module, so pypip, the module load pypip, and then pip install, and then you'd specify user, and you'd put in a package name. So you could Seaborn, and then you could see what happened and where it was installed. You could also install with Conda as well into a local directory that would do it in software, and it would just install in the standard Conda paths in that /software/project/project ID/user space, wherever you decide to have Conda be. More details obviously can be found on our documentation. And if there's some questions, first thing is the point of call is to look at Conda sites and pip. If there's something funny going on, but then of course, feel free to contact us as well. Now, R is another package manager. And so it can be used to run, it also is an interpreter language editor. We also suggest to not use Spack to install R packages. Again, you'd use Conda or the R internal package manager itself, so module load R, and then run R to install in a local space the package you want, such as, in this case, BPA is our example. So you make sure you module load R, you provide the R module, but we suggest then using R itself to do the installation in a local user space, in the /software/projects, project ID username space. Same thing for Conda. So it's very similar to Python. So manual installation of software. This is maybe where it gets a bit tricky. It's specific to remember that before you try to manually build software, first of all, you need to understand the dependencies that are required for your software and check to see if they're already available on Setonix. Right? If they're already available on Setonix, at least normally you know you could do module load a few things and then begin a manual build process. If the dependencies are not on Setonix, check their complexity and see what versions are acceptable. Right? So if you require some package that's not provided by Pawsey, check it to see if it's available through Spack, pip, or Conda to do the installation. And by complex runtime dependencies, I'd really say, so you can look at an example here. We've provided the dependency tree as constructed by Spack for GROMACS. This package has a few sets of dependencies, but some packages are quite complex, like Trilinos, which has a very, very large set of dependencies. And this would be quite a complex and time-consuming task to manually build every single bit of this. And so Spack would, if your package depends on Trilinos and the version of Trilinos is not present on Setonix, our recommendation is to use Spack to build Trilinos and then proceed from there. Otherwise, you have to build the dependencies as well manually. So compiling in the HP programming environment. So the C, C++, and Fortran languages are supported, those are the ones that are very much supported. The three main programming environments are the GNU, Cray, and AOCC. The one that's available by default is GNU. And then we have the Cray compilers and the AMD optimized compilers. They're all accessed through the Cray wrapper compilers, which are very similar to Magnus. So for users of Magnus that were building software with CC, like lowercase cc, uppercase cc, and FTN, that still remains the same. That's how you access the underlying compiler that could be GNU, could be Cray, and could be AMD. Always use the wrappers to ensure correct compilation on Setonix. The programming Intel environment for Intel compilers is no longer available, so we don't provide the Intel compilers. And the compiler instructions and a larger set of optimization flags than is discussed here is outlined in our documentation. There are some key changes with Setonix versus pre-Setonix. So we still have GNU programming environments, and the underlying compilers are still, if you will, GCC, G++, and T-Fortran. They're newer versions of it, which can be set up to be produce software that's optimized for the AMD Milan architecture that is used the hardware that's on Setonix. The subtle difference from before pre-Setonix to now is that prior on Magnus, the Cray wrappers tended to automatically put in optimization flags and some OMP parallelization, so some parallelization flags. And these are not, this is not the case anymore. These are not activated by default. So OpenMP, for people who are using OpenMP, that is not activated by default when you use Cray wrappers. Optimization is also set to 0 by default. So pre-Setonix systems have these optimizations enabled by default with OpenMP depending on the compiler version, and it was different between different compilers and different programming environments. So it could reduce reproducibility. The Cray compilers now are slightly different. So Cray C, C++ is now built with the LMVM compilers, so Clang, Clang++. They have different sets of arguments now compared to the previous Cray compilers. Again, there's no optimization set by default, so OpenMP flag is turned off, optimizations are turned off. Pre-Setonix systems have OpenMP turned on and had actually -03 and OpenMP enabled. There's a subtle thing for Fortran in the Cray environment. So the Cray Fortran is not gone in a drastic change like the C and C++ compilers, which are now based on a completely different underlying essentially toolkit that generates the machine code. It's an updated version of the Cray Fortran compiler The flags remain the same in this case, and optimizations in OpenMP are enabled by are activated by default. In this case, they've tried to keep it the same because it's essentially the same. It's an updated version of that compiler. We still recommend using explicit flags and do not rely on default settings, because that way you're consistent for all the builds you could do if you switch from Cray Fortran to GNU Fortran or AMD Fortran. So the other change, the big change, is Intel versus now AOCC, and I'm going to be talking initially just about C and C++. So Setonix does not support Intel, right? We support AMD optimized compilers with associated libraries, and that is based on LLVM Clang. The full Fortran is not currently provided by AMD. So AMD does not provide a fully functional Fortran compiler yet. Future releases will add this in, and they're working through it right now. The compiler flags are the same as the standard LLVM compilers. So Clang compilers, there's no change. They have the similar arguments to the Cray compilers now, and the optimization is turned off by default, right? So there's no NMP and there's no optimization. And if you were using before iFort, right? So the Intel Fortran compiler provided by the Intel programming environment, there is no equivalent in terms of AOCC, but we just recommend migrating to GNU Fortran, actually. So we've got other programming environments. So we've got the interpretive languages like Python and R. Use Pawsey provided Python and R modules at this time. They provide core functionality, but you then need to use pip or other package managers and so on to install additional packages. We do not recommend using the Cray Python and Cray R modules. Other languages. So we have actually provided a couple other languages such as Rust, Golang, Java, Ruby, and Perl. There are modules for these. If you have source code that requires these languages, we just load the module and then build from scratch. Any other languages actually require bootstrap builds from source. We probably wouldn't necessarily put the time and investment unless we had multiple users asking for the same sort of language support. So building parallel codes. So this is something critical in building MPI codes. So HP Cray provides an optimized MPI library through the Cray MPitch module. This module is set up to have the MPI build specifically for the interconnect that is on Setonix and also optimized for that interconnect. So the Cray MPitch module must be used for performance and multi-node communication. And so if you were building software and you were before using your own builds of OpenMP or something else, that's not possible. That will essentially limit your ability to do multi-node communication and performance as well. So the example here is if you had GROMACS. GROMACS is a code that makes use of MPI, this message passing interface parallelism. Typically, if you looked at Spack installs, if you tried using Spack installs and tried just looking at on your own little laptop, a Spack spec, essentially a concretization, the dependency build of what GROMACS requires, it would often stick OpenMPI as the library that would provide MPI. That is incorrect on Setonix. We provide it set up so that this would not be the case. It would always by default look for Cray MPitch. But if you specified OpenMPI specifically for a build, realize that this will not function as you would expect. It will not make use of multi-node communication. We really strongly recommend using the MPI that's provided by Cray. Building OpenMP enabled codes. So pre-Setonix, Cray compiler wrappers were just enabling this by default. So you didn't necessarily have to think explicitly, I have to put this flag in, but that's not the case anymore. So there's specific flags you have to put in. They all happen to be very similar, thankfully. So the F OpenMP flag past the compiler, except for the Cray Fortran compiler, is the flag that enables OpenMP parallelization for code. Building with optimized libraries on Setonix. So we have provided a number of optimized math libraries and other libraries as well. But we recommend using these. Instead of building your own version of this particular library, try seeing if it's possible to use the modules that provide these libraries. So there's examples like FFTW3. So there's FFTW3 and an AMD optimized one that's specific for the Milan architecture. There's FFTW2 provided by Pawsey, which is an older API of FFTW, this fast Fourier transform of the West library, this fast Fourier transforms. We also provide math libraries through a couple of different modules. So BLAST, LAPACK, SCALAPACK are commonly used interfaces. There is Pawsey provided ones like OpenBLAST, NetLib, LAPACK, NetLib, SCALAPACK. There's a few other versions of this as well. There's also an AMD set that are specifically for the Milan architecture. They don't necessarily provide all of the functionality that would be provided by the above, OpenBLAS and netlib and so on, but they do provide quite a large set of the BLAS, LAPACK, and ScalaPack functionality, not almost all of it. And they are optimized for the Zen architecture. And there's even an AMD optimized math library. So any code that makes use of just simple math functions, right, like cos, sine, and so on, you might benefit from using the AMD optimized, Milan optimized math library. So compiling from source, right? So we have provided a couple of configuration systems as modules like CMake, AutoConf, and so on. So you have to load these modules, or they're already in the system. So they're by default provided in the system. There's no module required. So AutoConf doesn't require any module loads, but CMake does. And the idea would be you can use these build tools, just make sure that you actually use the Cray wrappers correctly and point to the appropriate paths, such as /software project ID username. That's all encapsulated, by the way, in the my software environment variable, so you can just use that. So here's an example of trying to build with CMake, where you would call CMake. You'd make sure that the CMake install prefix is the my software environment variable and then some desired path for the software. The key thing is to make sure you use the compiler wrappers and not the compilers themselves. So like use CC, capital CC, capital FTN for Fortran, C++, and C. And the same thing goes for configure. Make sure you use these compiler wrappers to start building. If you didn't have a configuration system, so this is where you have, so let's say some either simple rudimentary make files, or even just a complex one, or explicit compilation. Again, just make sure that you use these compiler wrappers, CC, CC, capital CC, and FTN. Now, one thing we do recommend to mimic what is done by Spack, and some of the builds that we do as well for Pawsey, is to use rpaths for libraries and dependencies. So in migration module 3, I mentioned this, but I'll just go through it again, that at runtime, a particular software may depend on some library, and it loads it at runtime. And then what it will do is it'll try to find either the first instance in the set of libraries that are available that provides that functionality. So, or you can tell at build time, look here at this specific path for this library. And that is the use of rpaths. And our use of rpaths ensures reproducibility when loading libraries. You don't have to worry about if I module loaded this library and then I module loaded another library. The example would be for BLAS, LAPACK, and ScalaPack. You could module load OpenBLAS and module load netlib ScalaPack. They provide, and netlib LAPACK, and they provide libraries that are essentially the same, just different builds, different optimizations, but the functionality that they provide is the same. And then if you built with those libraries, you might not know which one you're using at runtime. So the best practice on Setonix is to make use in compilation of rpaths to a specific path that you want for that library. And then that way you avoid any issues with runtime differences. So for more details in use of rpaths and also compiling, please see our documentation, which is far more extensive than what is presented here. So the best practices, again, to just reiterate, is to use compiler wrappers, is also to ensure that the Cray x86 Milan architecture module is loaded. So this is loaded by default. This just sets the compiler wrappers to know that they're going to try to build software optimized for the Milan hardware architecture. And the recommendation is also to compile on the same nodes that you're going to where the software will run. So on the current phase 1 of Setonix, the login nodes and the compute nodes happen to have both Milan CPUs, have the same hardware architecture. But going forward in future upgrades to Setonix, specifically phase 2, there'll be slight differences between the hardware that's on the login node versus what's on the compute node, like a GPU node. So the recommendation is request an allocation on a compute node and build on the compute node. So it builds on the architecture of the compute nodes you'll be running the software on. So software development tools. So Pawsey provides a couple of debugging profiling tools to assist with development of developing HPC codes. There are debuggers that which control the execution of the code to identify the location and cause of bugs in the code. Pawsey provides debuggers as modules like GDB for HPC and ARM DDT, which is through the ARM Forge envelope. This is a debugger. Therefore, there's a lot more information about debugging in our documentation. And there's also profilers, which analyze their code to understand performance and insight and how it might be optimized. And there's a few tools as well. Some are Cray specific. So Cray tools require the Cray programming environment. But they do offer some nice analysis of how the code runs, like perf tools and Cray stat. There's also ARM Forge that provides map and performance reports that can work with multiple sets of compilers. Again, for more details, please see the profiling documentation. So how do I get help? And if you're stuck, well, again, as I've mentioned several times, the documentation has got extensive, it's got extensive documentation, but it outlines extensively how to build software manually, some of the pitfalls, some of our outline of the best practices when building software on Setonix. This migration video and other related migration videos will also be very useful. And there's always the help desk as well for building software. Now, I should reiterate, in terms of software practices, we it's up to Pawsey's discretion to help build software tools that are essentially user software tools. So if you're building your own software, you can obviously ask for help. But depending on the complexity of the request and the common usage of the tool, if it's just you, we might suggest that we'll provide some guidance, but it will be up to the user to actually build the software. Special consideration is given for some specific projects, like if it's an uptake project, or if it's one of the PACER projects, some strategic projects. So if it lines up with strategic goals, we might provide more assistance. Regardless, please feel free to raise a ticket. Thank you for listening. Have a great day.